let me see this. And this one also is going to generate a flux. Going this way also, right? Right? Flux is going to be like that, correct? Agree or not? See, if I have this one here, the flux is going to go through the iron here, coming through the air gap, going this way, right? The arrow of the top. Oh, no, you cannot be this way, you have to be this way. Right? So you can understand this one, right? Because it's very important. And here is the theta, right? Doesn't matter where this one it is. Let's say it's here, over here, over here, over here, over here. Does it change the reluctance of the circuit? No. Because this air gap everywhere is uniform, right? Doesn't matter where this one is standing. This is the axis of this winding. It could be here. Let's rotate it 90 degrees. It's going to be here, right? But the resistance like this one, the air gap is not going to change, right? Right? So this one, which winding is this one? Is the S, right? If the reluctance doesn't change, how much is the inductance for this one? LSS? It's going to be NSS, right? It's going to be NSS, NS to the power of 2 over whatever is the reluctance, right? R theta, right? R theta is constant. This is a LSS theta, right? But this one doesn't change the theta, right? So this one is constant, right? You're looking very missed. Which part did you get? Did you understand that one?
Yes.
That one you understand?
I got it. Because
Okay.
the delta doesn't change.
Because the air gap doesn't change here, right? If you want to draw the magnetic circuit for this one, it's going to be like this. Yeah? You have one R here, one R, small R here, right? One R here, one R here, right? And one R here, right? And there is a source here, right? This one they don't change, right? This is fixed. This is RG, R rotor, RS, RS, right? They don't change, right? Doesn't matter what rotation you are, what position you are. Yeah.
So theta is the angle difference between the rotor and the stator, right?
Yeah.
So right now we're assuming that the slip isn't.
There is no slip.
There's no slip.
This one,
Okay.
let's not talk about the slip, but this is synchronous machine.
Okay.
There is no slip. But my point is, we define theta between this axis and this axis. My point is, doesn't matter. See, this one is perpendicular to this one, right? If this one changes this way, this one is going to be here, right? This one doesn't move, right? This one is fixed. But this one is going to go this way, right? Now, so if the reluctance doesn't change, what does mean LSS is constant, right? I will put it for road now. Put it for road. Right? Again, the flux is going to go like this, right? So this one rotates, the whole flux is going to rotate with this one, right? But the magnetic circuit is going to be all the time the same, right? If this one goes to the 90 degree, it's going to be like this. If you go to the 90 degree, let's go to the 90 degree. Basically, this one is going to come here, this one is going to be here, right? Now the flux is going to be like this. Right? That's the whole shape just right and rotated 90 degrees. My point is, see this air gap and this air gap, they are the same, right? So it didn't change with the theta, right? When it rotate, it didn't change the air gap, right? So LRR is not a function of theta, right? It's a constant. So LSS, LRR, they're constant. They're not function of theta. That's enough. Now let's start to think about LSR, LRS. Mutual inductance. It does show how this winding, how much they are linked together. They are connected together, right? Look at here. for example, here we have some flux going here. Part of it is coming from here, right? It does show how much of flux here is coming from here. How much this one is linked to this flux. The same thing here. How much of flux here is from this winding and how much is from this one. They are linked together, right? They are kind of tied together. Somehow they are getting together, right? Tell me how much these two are tied together. It's a projection, right? I want to know how much of this one is going to go through here. Projected flow, right? It's going to be FR cosine theta, right? Right? See, what was here? What did I talk about here? I said, okay, I have, 10 Weber. Out of this 10 Weber, 2 Weber goes here, right? This one is going to define the L12, right? What did he say? He said 10 Weber here. I said, don't care about here. Calculate how much of this 10 is coming here. How much came here? 2 Weber, right? So it's going to 2, when you're calculating this one, you say 2 divided by that current, right? How much of flux here is coming from this current, right? How much of this flux, this is the magnetic flux, right? Is going to this one. Projection of this one, right? You have 2 vectors. How much they are connected together, how much they are correlated together, projection of that, right? So LSR is going to be something cosine theta, right? LSR. We call it LSR. This LSR is fixed. This one is a fixed, right? This is a fixed number, time cosine theta. So now if you go look at the homework 2, problem 3, problem 6, just go think about it. It said MAF is a cosine theta, M cosine theta, a constant number time cosine theta. MBF is M sine theta. The reason is sine theta because A and B, they are 90 degrees far from each other. But go think about it the way I explained it here to see you can easily get those numbers. I gave you those ones, you don't have to even calculate it. But to see if you can calculate it yourself. It's going to be like that. To make this problem very difficult, they call this one cylindrical machine. Cylindrical because the rotor is like a cylinder. Remember? They have a solid pole machine. For example, this one is like this. Right? The rotor is not full cylinder. Now, theta is important because if you are here, right, then you have this one, flux is here, right? Flux, let's see here. Flux is here. But based on what position is this one, it is like this. You're going to see different again. LSS, LR, this one, this guy, they're not constant thing. But forget that, we're not going to talk about that. When it's cylindrical, just think about it. It's a very, very simple rule, very simple rule. If this guy is cylindrical, self-inductance of this one is constant. If this one is cylindrical, self-inductance of this one is constant. Got it? If this one is cylindrical, LRR is constant. If this one is cylindrical, LSS is constant. If both of them they are cylindrical, both of them are constant. Look at it here. Here, is LRR constant or not? Why? Because the stator is cylindrical, right? LRR is constant, but LSS is not, because this one is not constant. It is not cylindrical, right? So now forget all those things about the solid pole machine. Let's go through this example. That was the difficult part. The rest is easy. So how much is the co-energy? Right? Right? That's two systems. L11, I1 to the power of L22, I2 to the power of L12, I1, I2, right? How much is the torque? See, this is a rotating machine, you're going to have a torque, right? Right? is going to be, we said this current are constant, so for this, it's going to be DLSS over d theta plus half of IR2 DLRR over d theta plus half of, not half, LSR. Sorry, it's going to be IR, IS, DLSR over d theta, right? Right? How much is this one? Zero, right? So how much is the torque? It's going to be IR, IS. Take a derivative of this one. It's going to be LSR minus, there's a minus, because this is a cosine, right? Sine theta, right? Let's write it down. IR is going to be minus IM, IRM, ISM, you can call it ISM, LSR. Let's put all those things here. Cosine of omega t plus alpha, cosine of omega t, omega RT, cosine of omega st, and cosine k, sine k. How much is theta? Theta, somebody tell me. Omega mt, right? If the machine is rotating with omega n, right? So we have three. Omega r for the rotor field, omega s for the stator field, and this rotor also is rotating, right? Omega m, right? Now, right, all these things after a lot of calculation, you're going to get, let's call this one m. Don't call it LSR because you're going to get confused. Call this one m. Call this one m. Call this one m. If you do all this calculation, it's going to end up here. But I want to discuss this one, and for those who are really interested in electric machine, this is a very good example. If you do everything, so T is going to be ISM, ISR, M over 4. Now look at here. This is a little bit too much. I'm going to write sine of omega m plus omega s plus omega r t plus alpha. Oh, okay, all there is alpha. That's what it is. What I'm going to do for s. So plus sine of omega n minus omega s plus omega r t minus alpha plus sine of omega m plus omega s minus omega r t minus alpha plus sine of omega m minus omega s minus omega r t plus alpha. So this one is going to be a torque equation. After simplifying everything, we are going to get here. Now, this is the last part. If machine wants to rotate continuously, what should happen? The average of torque should be non-zero, right? And you know this. You know this one from power electronics or whatever course. If you have a sine function, how much is the average of sine function over one cycle? 0. So you should check how you can have a non-sinusoidal, right? So basically, either this one should be 0, right? Or this one should be 0, right? One of this one should be 0, right? Because if it's not 0, sine of something t plus alpha, how much is the average of that? 0, right? You put this one equal to 0. You put the coefficient of the t for all of them equal to 0. Any of them happens, means t is going to have a average of not 0, right? So basically, I said either omega m plus omega s plus omega r should be 0, or omega m minus omega s plus omega r should be 0, or omega m plus omega s minus omega r should be 0, and omega m minus omega s minus omega e. One of them can happen. All of them cannot happen, right? One of them can happen. So if you have a sine waveform, let me do this. Sine of 377t plus 60. How much is the average of this whole this is one of them should be 0. This one, or this one, or this one, or one. One of them should be 0. Right? How much is the average of this? 0, right? We don't need to think what is 0, right? This is fine. Right? On one cycle, average of sine is 0, right? You have to use this one 1/4 power sine calculation, you know, right? You do the full wave, half wave, those kind of things. Use this one a lot. You should be expert by now to calculate those kind of things, right? So, but how about average of sine 60? How much is the average of sine 60? Sine 60 is up 2 over 2, I think, right? I don't know, 1.85, right? If this one is 0 somehow, right? I have some average value, right? If I want to have for the motor to rotate, this one, average of this one cannot be 0, right? If average of this one is not 0, either this is 0 or this one is 0, what of these four, right? So this one we can kind of summarize it all these cases, and we can say omega m can be plus minus omega s plus minus 0. Machine is going to rotate as one of these two. Either plus that, either minus that, or we can go other way. Plus omega r minus omega s, those kind of things. And how much is the t average? Somebody tell me, how much is the t average? Forget the sign because it's going to be either positive or negative. How much is the t average? I guess M. This one should be IR. M over 4 and what? Sin up. Let's take it this way. It could be either positive or negative, right? This is synchronous machine. The problem number 6 is the same way. It's a little bit more calculation. I was going to talk about that problem number 2, but forget it. Good luck in your midterm. Just please read your homework, and if you need extra problem, chapter 1 and chapter 3 of the book. They have lots of problems at the end. You can use those one if you want. They're pretty good problems. I'll see you in 2 weeks.
Time for ice balls.